What do we have to prepare for UB hacking? You're not supposed to prepare anything. You're supposed to come there, ideally with a project idea that you and your team want to work on. You should be prepared with a team, talk to other people going. Or, being virtual, it'd be really tough to find a team while you're there. Or maybe they have some logistics that'll make that easier. But you should have a team and a project idea, and that's it. And then you build that project while you're there. Yeah, genetic algorithm. Well, I want to get into the lecture, but maybe in the 20 minutes after we can talk about this. I haven't formally introduced genetic algorithm. I usually don't introduce any of the homeworks anymore because we have the videos especially. I can talk about it when we have time, but not during lecture time. So, immutability. Can you just go and watch? Yeah. For UB hacking? I don't know. I haven't looked at all their logistics this semester, how that's going to work online. But, it might be easier to just go and watch. Just enter the meeting and do it. Oh, the deadline for a genetic algorithm. I'll look up this just because I don't remember. I don't think I put a deadline in the document. I don't put deadlines in documents anymore. But whatever it is on the schedule, functional programming, November 1st, that's already pushed back a week. It's usually due the week after. So we finish a learning objective, and then the following week, week from that Sunday, that's when the homework's due. So you get an extra week to do the assignment. After I covered all the material you'll ever want for that assignment, you have a full week to digest everything and really do it. You really should be doing the homework throughout as we're learning the learning objective. But I give you the extra week because, students don't start early. But anyway, let's get into some lecture content. What's up, Trino? Oh, Grudge. Yeah, no free pizza this time for UB hacking. Unfortunately. Okay, let's talk about immutability. This is something that I kind of mentioned throughout the semester, but this is the first time where we're going to address this topic head on and explain what we actually mean by immutability. So, the lecture question today, yes, lecture questions make a big return every lecture from now on. Not now on, but until the Friday before fall break, actually. Then you have that week to, do whatever, hopefully catch up. And then 2 weeks, and it's the end of the semester. So you have 3 weeks, if you count the break, of no lecture questions to catch up on everything. But today, another day, another lecture question. So we're still banning var. This lecture question, the homework, the genetic algorithm homework, and Friday's lecture question, var is still banned. And then after that, no bans for the rest of the semester. The last 12 lecture questions, it's whatever you can use to get it done. Only during OOP and functional programming do I ban stuff, just to force you to use the things that I'm teaching, that you're supposed to be learning. So, banning var, banning any mutability or any way of simulating variables. Also, make a point class with a constructor that takes x and y as doubles, so we have a two-dimensional point. And then 2 methods, add and multiply by scalar, that do what you would expect them to do, adding 2 points component-wise, and multiplying a scalar in each dimension. And then a test package named test point. For this, actually I should have updated this, but I'll give you the warning here. Point is an object, a class that exists in various packages. So when you're importing point in your test point class, make sure you're importing functions.point. Make sure you're importing the right thing. Because if you just do point and then rely on auto import, rely on the IDE to do your imports for you, like I do, be careful. Make sure you're auto importing the correct thing. I don't just randomly click the first thing. Make sure you're importing the correct thing. Actually, let's try this. We can do a quick test of this. Where am I? Right here. val p1 of type point equals, let's just equal that. Oh, I forgot on this machine. It should be this. I can't even do auto import on this one. Oh, there we go. So the first suggestion is going to be Java auth point, and then you have all these other point classes. Make sure you're importing functions.point. Oh, week 7 functions. I better not have the answer in here. Nope. It's a start, but you don't have the rest of it. So make sure you're importing the right one. I've seen so many students fall into that. They just want the ID to do everything for them. There is a line where the ID can't really help you out. When it has multiple choices, it's going to usually choose the wrong one. So make sure you're testing functions.point and build this functionality, test this functionality. The key here is that var is banned, so this is an immutable point. You have the keyword val for x and y for the values. So how do you make a change to a point if you don't have any variables? How do you change those values? And the answer is to create a new point with the values that you want and then return that new point. So tracking the way references are moving around your program is important. You don't have to check the references directly for this one. You can check the x and y components, but you got to make sure that everything's working the way you expect it to. What does the $sign do? What did I do with the $sign? Oh, that's formatting. So I want to print out a point, I only want to display 2 decimal points, 2 values after the decimal. So I'm using some formatting syntax there. That's in the handout for genetic algorithm as well. It's just so when you have those truncation errors for doubles, you don't see the 0.4999999. I just don't want to see that kind of garbage. So I round it to 2 decimal places, only for display purposes. I did the same thing in the calculator handout code. I use that same syntax. You've seen this before, assuming you're doing the homeworks. Okay, so immutable objects. The concept here isn't too crazy. It's the implications of this concept that we'll spend most of the time talking about. The concept is you have an object and its state can't change. None of its state variables, the values cannot change. So we don't technically have state variables, we have state values only. And that's an immutable object. That's it. So let's talk about the implications of this and how we use things like this. The immutable objects are still on the heap. They still behave just like objects, except we can't have the state changing, which the reason why we would want this, and I'll talk about this a little bit in a future slide too, is that the state can't change on us. So we're still passing this object by reference. We're giving references of our object to the methods, to any methods that we're calling with it, except that method cannot change the state of our object, which is an advantage. Depending on what we want to do, it's an advantage of knowing that our object won't change. We give this reference. We usually have to worry about the function, the method, changing our state variables, messing around with our variables, and changing the way that object's going to behave. But now we don't have to worry about that. If it's immutable, nobody can change those values, so we don't have to worry about it. So we can share our objects, references to our objects all over our code with no worry that anybody's going to change the state of that object. So that's the advantage of this, of immutable objects, is that the state can't change. But then we have this situation of, well, what if we need that state to change? What if we need a state to change? And the general solution here is to create another copy of that object with the changes applied. Add a new object to the heap, and then return a reference to that one, to return a brand new reference. Compare. So here's an example of that. This is a class that we're using to simulate a counter. I have some integer value, some initial value, and I can either increase or decrease that value, and I have a way to access that value through this print count, which is just going to print its value to the screen. I'm artificially restricting access to the counter completely. So we can't even say, we can't even get the value. There's no getter, there's no way to get this. I didn't use val or var here, so I'm artificially restricting. This isn't something you normally do. I'm just doing it to force some recursion here. But you can't even read the counter. So the question becomes, how do we increase and decrease? Well, we're going to create a new object of type immutable counter and increment or decrement that counter based on the method that was called. So we're actually returning a reference to an immutable counter when this is called. So if I say immutable counter, I have a reference to an immutable counter and I want to decrease it. Decrease is creating a new immutable counter on the heap with that value decremented, that change applied to it, but a brand new object, and then returning a reference to that object. So I return a reference to that object, and now I successfully kind of simulated a decrease, but I did it by creating a brand new object and still keeping the original object, but creating a brand new one with that change applied to it. So what if we want to do something like decrement 10 times or increment 20 times like we're going to do in this example? Now normally we would just say whatever the value of counter is, give me a new immutable counter with that value minus or plus 20. But I'm restricting that just so I can get one more example of recursion in here so we can get more practice with recursion. Say we can't read the value of counter, all we can do is access the increase and decrease methods. That's the only way we can kind of simulate these changes, by creating a new counter either incremented by 1 or decremented by 1. And we're still banning var, so how would we, actually we don't even need var ban because we can't access the counter. So how would we do that? Or no, yeah, we do, because we would use a loop otherwise. Let me skip a slide here. I forgot, I'm getting ahead of my slides on this one. So what if we want to increment or decrement 10 times? We would normally just throw this in a loop that iterates 10 or 20 times, however many we want, and then continually, say var counter of type immutable counter equals new counter. And if we want to increment it 20 times, we would have a loop that iterates 20 times, and then say counter equals counter dot increase. That's how we would do it with a loop. But if we're banning var, which is the purpose, which is a means to the end of forcing recursion, we're forced to use recursion here, which we are because we can't access the counter and we can't use var. We're going to have to set this up recursively. So our recursion, we're going to take some value of the number of times we either want to increment or decrement. If this were negative 20, we would decrement that many times. We would call decrease that many times. And the counter that we want to increase or decrease by n times. So our base case in this is going to be n equals 0. Well, if we have a counter and we don't need any change made to it, just return it. There's nothing to do. No work to be done. There's nothing, what are we going to do? So that's our base case. Trivial input, output. If n is 0, just return the counter. Done. Else, we have to decide, is n positive or negative? If n is negative, then we're going to call decrease by 1 time and then increment n. So say n is negative 10. I see that n is negative. I'm going to call counter.decrease. So counter is going to be decremented by 1. And then n is going to be increased up to 9. So we're going to say, okay, I need to decrease this counter by 10 times. Let's decrease it 1 time. And then make the recursive call and say this still needs to be decremented 9 more times. Then that recursive call is going to say, okay, let's call decrease 1 more time and say that it still needs to be decremented 8 more times. We'll have negative 8 as n. Then negative 7 after call decrease, negative 7, call decrease, negative 6, call decrease, negative 5, so on until we hit 0. By the time we hit 0, that decrease will have been called 10 times throughout all the recursive calls. So if I call decrease, if I have some negative n and I call decrease on it once, the recursive call of n plus 1 after with a new counter that's been decremented 1 time, all my logic is sound and I'm getting closer to the base case. So we have all our ingredients for good recursion. If n is positive, like in this case of 20, we're going to call increase one time and then make the recursive call with n decremented once. So if I have a counter, I need to increase 20 times. I'm going to call increase once and then say, okay, increase this 19 more times. Increase it again, increase this 18 more times, and so on until increase is called 20 times as we hit the base case of the recursion, and we hit 0. And we have, and we're returning a counter that's been increased 20 times. And when we hit print here, counter has never changed. It's immutable. It's always going to be 10. That state cannot change. So print count, this is going to be 10, the initial value, and then counter 2, the new one that was returned through the recursion, that print count is going to print 30 to the screen. But it's going to be a completely different counter. So in this program, we've put 31 counters on the heap. We've created 31 new objects, and then we're really concerned with these two as our end results. So notice our recursion, our base case, trivial input output. Each recursive call, the logic is sound, and we're always getting closer to our base case. N can be negative or positive, but based on whether it's negative or positive, we're still getting closer to 0 with each recursive call. So let's sit on this for a little bit. For loop with extra steps. I like Ellipso's comment the most. Ellipsio. I get this. I like it. I don't know, Zianatri, I don't know what you mean by a for loop with extra steps. It's kind of what recursion is. You could think of recursion as a for loop. You can get the same things done with recursion as in a for loop. But they're kind of different ways of tackling the similar type of problem. You need code that executes a variable number of times. What if we don't want to go to 0? I mean, that's the way this is set up. Like, if I want to increase 20 times, I would have to go down to 0. Change the base case or have a third parameter with the base case? Sure, you could do that, but yeah, have a third parameter with the base case, and then say if n equals the base case, or if n greater than the base case, or if n less than the base case. You know, you could have a variable base case like that. For this specific example, I don't know how much sense that would make. Maybe if you had 2 counters and you wanted to, and you wanted a reference starting at the first counter, decrement it all the way down to the other one. Maybe we could set up something like that. But yeah, there's no limit. I mean, this is a pretty straightforward example. That's why I use it for lecture. But there's no limit to what we can get done. We can set this up in all kinds of crazy ways. How do we pull the actual value then? For this example, I've restricted that. You can't actually access the variable counter from outside of the immutable counter class. I did that on purpose just to force immutability and recursion and all the goodness that we've been talking about. But I did add this one method just so we can see the value of counter, just so you can still print it to the screen and see it, or else the programs wouldn't be, you wouldn't be able to check anything. But like, you wouldn't be able to write test cases for this the way I have it set up. You wouldn't be able to write a test case that says, is counter the right value? Because it's only being printed to the screen. Technically, you can capture standard output. You can capture what's printed to the screen, and that, but we're not going down that road. That's why, like, this wouldn't be a lecture question. I wouldn't give you this class and then say, write the code to increment, decrement. I did do that one semester, but it's, I realized the problems with it pretty quick once I released the question. What happens to all the unused objects on the stack? So the objects are on the heap. You got to get that straight. That's an LL1 thing. All those objects are in the heap, and we have references to them. As soon as we have an object on the heap that we don't have any references to on the stack, there's nothing on the stack referring to it, no references to that object on the stack, then that object on the heap is up for garbage collection. It's up whenever the garbage collector next runs, it's going to clean up all those and free up that heap space. Yeah, on the heap. Cool. All right. So let's see. We got 2 more examples today. This is, of course, the simplest one. So let's get a little more complicated and talk about strings. Strings are immutable. This is the reason why I don't talk about strings or lists. Lists are the last example. This is why I don't talk about strings or lists when we first talk about stack and heap. Because strings and lists, because they're immutable, this will be one of the big reasons, like why does this matter to me as a programmer? Strings and lists are immutable, so they are on the heap. They're passed by reference, but in many ways they behave as though they were on the stack, and that's because they're immutable. So these are kind of, to us as programmers, they're kind of have properties of stack and heap objects. But they are on the heap, and let's explore what that means to us. And yes, we're getting heap and stack back. So with recursion, we talked about stack and putting many frames on a stack as we unroll a recursion. Now we're talking about the heap again, and talking about how these references on the heap work with immutable objects. So that's why, for those of you who I said, if you didn't get LO1 lab complete, LO3 lab is a natural way for me to assess your LO1 stack and heap understanding. It's because we're talking about stack and heap again, baby. It's here. It's happening. So just implicitly, as I ask you on LO3, I'm going to say, here's a recursive function. Here's a recursive method. Talk to me about what happens as this runs, with highlighting what's happening on the stack and heap. Here's a program that uses an immutable object. Talk to me about what's happening on the stack and heap. That's what you can expect in next week's lab for LO3 lab, verification. That's what you can expect. So if you can do that, there's no reason for me not to give you credit for LO1. So for those of you who still don't have credit for LO1, you have another chance next week and the week after. I did change some of the schedule. I should actually mention this. This should have been at the top. But the Thursday lab, this Thursday's lab is not a genetic algorithm pre-homework. I did change some of the schedule. I made that post on Piazza, so check that out for a little bit more detail. But I replaced all the rest of the pre-homeworks with learning objective makeup labs for the rest of the semester. So like tomorrow's lab is an LO2 makeup lab. If you have credit for LO2 read, then you don't have to take a lab tomorrow. So just be aware of that. There's no pre-homework, but I did add details in the genetic algorithm handout that is containing what I would have had on the lab, but you don't get a grader for that. You're at the point where I expect you to be able to write your own tests and kind of test your own tests. You should be at that level of sophistication as a programmer at this point. So let's go through this example. Let's go through this one at a time. I'm going to skip some of the steps that we've seen last time when we talked about stack and heap. So we're creating a value named course. I'll skip it in the slides, I should say, but I'll talk about it verbally. So I'm creating a value named course of type string, assigning it the value CSE 116. This is an object. Strings are not primitives. They do not go on the stack directly. They are created in heap space. So I get this string in heap space at some reference, and I get a reference. This returns a reference to that string that was created on the stack, on the heap. This string goes on the heap. I get a reference. This resolves to a reference, and that reference is stored in this value course. So in the mainframe, I have this value named course that stores a reference to the string on the heap. No grader. Yeah, big boy paints on. You get your big kid paints out. There's no grader for the lab objectives. There's no grader for any of the testing for the genetic algorithm. So it's all, it's 1 or 0. Big kid time. So we have this reference. That's what's stored in this variable course. And then we call this method nerf, taking a reference to that string. So this is passed by reference. And we get all the behavior that we would normally expect from a pass by reference object. So we give a reference to this object to nerf. The only difference is that since strings are immutable, none of its methods or anything you can do with a string, you're never going to be able to change its state. So this string at memory address 1, Again, the memory addresses, the numbers are just made up. At this memory address, this will always store the string CSE 116. This will never change. And that's what it means for a string to be immutable. This reference, like no matter what nerf does, course that stores a reference to 1 is always going to refer to a string that's exactly CSE 116. Forever. That's what immutability means. So when I call this method, I don't have to worry about this value course. I don't have to worry about this method going to that reference and changing anything here because the string is immutable. Yes, that's right. CSE 116 is forever. Is forever. So when I call this method, I get the reference to 1. I call 1.replace 5 to 6. What this does, since this is immutable, is it doesn't change that string. It instead creates a copy of the string, creates a brand new string with all the 6s replaced with 5s. So I create a new string on the heap, we'll say at 2, containing the string CSE 115. So I create a brand new string with the change reflected, but since this method returns unit, I never actually get a reference to this string. So this at 2, what I like to say, this is just thrown on the ground. You just leave it on the ground and walk away from it. So we created a brand new string, resolved to a reference at 2, but we never stored it in a variable. We didn't return it. We didn't do anything with that reference at 2. And then we end the method which returns unit. So nothing is returned, and we no longer have a reference to this string that we created on the heap. So we created a brand new string, but we did nothing with it. I'm sure most of you have made this this mistake before. You call like something like this replace, and you expect input to be different after it's called. The reason why it isn't is because the string is immutable. The replace method does not actually replace 6s with 5s. It creates a brand new string with that replace taking effect. So you would have to say, like if you want it wouldn't work inside here because the inputs are immutable, or values, I mean. But if you did course.replace 6.5 here, you would have to do course equals course.replace 6.5. You have to reassign the reference. So I'd have to reassign the reference at 2 to this value course, which of course I can't because it's a value. But if I had this as a var, I would have to reassign that course equals at 2, which would be the return of the replacement. So we would have to do that change, that replacement, if we want that change reflected. So this is why if you're iterating over some values and adding a value to a list, for example, for each iteration, that's why you always have to say my list equals my list append whatever. You always have to reassign because you're reassigning a new reference to the newly created object. Yeah, I mean, there are mutable and immutable. So there's mutable versions in Scala, but if we're talking about immutability and you're learning about immutability, it kind of defeats the purpose if you're using the mutable versions of things. With strings specifically, I'm not aware of any language that has mutable strings. Strings are, or I shouldn't say any language, but like, but it's common for strings to be immutable. Yeah, it's common for strings to be immutable in most languages. I'm still saying it. Not most languages, but like Java, Scala, I believe Python, I think JavaScript, all have immutable functions. So the languages you would have been exposed to by now. If you mark it as var, you could do different things. Oh yeah, that was before I said it. Oh, JavaScript does have different for strings. Okay, it's good to know. P. How does replace load the content and create a new reference? So replace is going to call the replace method, which is part of the string class, with input as the reference in the keyword this. So inside the replace method, we'll have the keyword this referring to this input, and then it's going to create a new string with that replacement. You know, it's worth, shifting gears a little bit. Oh, come on. Give me there. There we go. It's going to be unreadable, isn't it? Place all. So we get a reference to a string. Oh man, where did text come from? Okay, well. Oh, that's if. Oh, I see. So it's going to use a Java string buffer, which is a way to build strings, kind of simulate. This is actually the Java's way of simulating a mutable string. But we're going to create a new one, do the replacement, and then return that new string buffer .toString. So convert that to a string, immutable string, and then return that. So that's what the replace method is doing. It's calling this replace all, takes a reference to that string, creates a new string with the change applied to it, and then returns that new string. Oh, I was looking for the keyword this. That's what I was looking for. That's a static method, isn't it? No, it's not static. All right, I gotta give up on this. I give up on that one. I wanted to show the keyword this, but it looks like it doesn't. Just the way it's set up, it has some helper methods there. So the string @2, that's still in the heap, but we don't do anything with it. We return unit. When we end this method call, the state of the stack is exactly the same as it was before the method call. And this reference @1 that we have refers to a string that's in the exact same state as it was before the method call. This return unit, this is something you should never see while we're embracing functional programming. The only reason to call a method that returns unit is for the side effects, meaning because it changes the state of some object, even if that object is, even if that state is the state of the console printing something to the screen, it's changing some state somewhere. We don't have any state in pure functional programming, so you should never have something that returns unit. I guess except main maybe, but main should return unit. But other than that, nothing should return unit if you're embracing functional programming. So let's move on. We call this Amplify method. Oh, and since there's no references, this is a side note. I don't expect you to know about garbage collection. Maybe it's something I'll add to the course sometime, but the course is stuffed as it is. So this @2, we no longer have a reference anywhere on the stack to this object. So that means it's going to be eligible for garbage collection. Next time the garbage collector runs, it's going to see that we no longer have access to the string, and it's going to sweep it up. It's going to destroy that and free up this heap space, depending on however it's optimized and how the garbage collector is working for that specific program. Probably going to collect it as soon as it runs. So now we get to this. Now we get to this amplify method. We're going to say amplify, of course. Now this does return a string. So when we call input.replace, we're doing the same thing we did before. We're taking the reference input, which is assigned the reference course, which is on the stack, which is @1. So we're getting this string as input. A reference to this string is input. We're replacing 116 with 150. So we're creating a new string with that change reflected. We're creating a new string, putting that on the heap with that change. And then now we're actually returning that. We're not returning unit, we're returning a string. And this is the last expression that's evaluated in this method call. So we're going to return this new string @3 with that change reflected. Now the method ends. The input, the parameters and local variables and everything for this method call are destroyed with the stack frame, but we are returning @3. That's going to be stored in this new value data structures, and now we do have a reference to this new string. So again, we still haven't changed or modified or done anything with the original string. So course, that's always going to refer to a string with @116 because strings are immutable, and this is a val. So there's no way for anything to change with that. But we did create a new string based off of that one by calling a method of 116 of this string and stored that in a new value called data structures in this method. Now we get to this next line. This is a similar to this one where we're computing something, we're doing some work, but then we're just leaving it on the ground and walking away from it. This is very common in 115. I always have to teach students 100 times in office hours this one. It's a tough one to grasp at first. But here we're taking course, appending a string to it, calling the append method. That's going to, again, create a brand new string on the heap and return a reference to that string. So this resolves to this reference at 4 in this example. But we can never access this string. We can never do anything with it in our code because we're not doing anything with it. We compute it, and then walk away from it. We don't store it in a value or a variable. We do create the string, but since we don't do anything with it, we just don't get to see that change. So this isn't going to append is great to the string referred to by course. It's going to create a new string with those two strings appended to them, and then walk away from it. And it's worth noting there are actually more strings on the heap. I didn't show all of them, but space is great! Exclamation point. Like that is creating another object on the heap. So we would have an object for that. We would have an object for 6 and 5. Those would be on the heap. 116 and 250. Those would be on the heap. So we would actually have more strings. Every time we have a string literal, we would have more objects on the heap, more immutable strings. So I didn't show them all in this program, but there would be more created. Now we're going to do something similar. We're going to create a new string is fun, put that on the heap, concatenate that with the string at course. 116 is fun. I hope you all agree. I think you will. And return a reference to that new string. So we create a new string, return that reference, store it in a new variable. Now we have these three values, not variables. We have these three values on the stack, all referring to different strings that have been created throughout the execution of this program. So if a value never changes, why store it on the heap? The short answer is because it's not a primitive. The longer answer would be the compiler wouldn't have, and the JVM wouldn't have a good way to optimize that and to store it on the heap. So what if we create a string that's, here's a good example. What if we create a string that's 1,000,000 characters long? Certainly within our right to do that, but we're probably going to overflow the stack if we're on the stack. So we put it on the heap where we have more dynamic memory, where the memory can be created and destroyed and stuff. Primitive byte, you're going to have to go back to one of the earlier lectures on that. So primitive, that's the Java term for it. I use that to refer to any values that go on the stack. The Scala term for that would be any object that extends any val, the any val class, which are booleans, ints, longs, doubles, chars. Byte is your name. Would go on the stack. And that's what I refer to as a primitive. Everything else goes on the heap. And then we print these things to the screen just so our program does something. If you run it in the examples repo, it does something. It just prints these things to the screen. And notice at 2, at 4, we don't have references, so these might be gone. These might have been garbage collected. All the string literals we created on the stack, those are probably all garbage collected. They might be. This program's so short, the garbage collector might not even had a chance to run, actually, to be honest. But those are all eligible for garbage collection. But 1, 3, and 5, we print those things to the screen, and that's the end of our program. I think literal as variables. So string literal or like an int literal, it's just when you have a literal value in your code. So when I put quotes CSE 116, this is a string literal. It's, I don't know, literally a string. Or if I just type 5 as an int, that's an int literal. It's just a value. It's literally a value. It's not a reference to, well, actually, I guess this is technically a reference to a value too. but it's not a variable or a value. Like course is not a literal. It's a name to a value that we gave that's storing a reference to a string. But if we just literally type out a string in our code, we call that a string literal. Yeah, primitives are... So anything that you can have a literal in your code... Oh, that's not true. I was about to say is a primitive, but that's not true because we have string literals, which are not primitives. But it's close. Except for strings. I would guess string is the only exception to that. Like if we type the keyword false, like that's a Boolean literal. Yeah, except strings. Lists aren't literals though. Lists, you're calling the list constructor to create a new list. And technically we're doing the same thing here. We are calling the string constructor, but strings, you know, they get some special syntax. There's something we use so often in programming that they get some special syntax. Oh, we only got 10 minutes. Lists are immutable. So strings and lists, these are the two things we've been using all semester that are immutable. So these are the two I want to highlight. And I'm going to highlight the list through this program, which, looking at, I wasn't watching the time. I wish I saved more time for this. So we want to find the first n primes. Here, in this case, 3. So this program, we expect to print out 5, 3, and 2. Or 2, 3, and 5, but the way I wrote this code, it's going to print 5 first. It's going to start at the largest prime. So we want to compute and print the first n primes, however many primes we ask for. So to do this, let's just go through the code real quick. I have a base case of if somebody gets smart and says, I want 0 or negative primes, I'm going to return an empty list just so my code doesn't break. If somebody says, give me the first -5 primes, you get the empty list. Congratulations. If n is 1, I have my legit base case. Return the list containing 2. The first prime is 2. Done. End of story. First prime is 2. Trivial input-output behavior. If you're asking for the first prime only, that's 2. That's it. That's the first prime. Else, we're going to enter our recursive step. And I'm going to get the first n-1 primes recursively. I'm going to assume that's correct, and it gets closer to my base case, so I got my boxes checked. The only thing I have to do now is with this recursive call that gets me closer to the base case, I have to make sure my logic is sound and that I get to the next case. So if this computes the n-1 first n-1 primes, then I have to, my job here is to compute the nth prime given the n-1 first n-1 primes. So my task here is to find the next prime. Given the first n-1 primes, find the nth prime. That's what my recursive step has to do. That's the work that I have to do here. So first, I'm going to compute the max prime. Max, another one of those nice methods that we can call on data structures. Just .max, give me the maximum value based on the default comparator. These are ints, so the max value is going to be the largest value int. That's the largest prime that I've already found. And now I'm going to call this other recursive method find prime, which I snuck in 2 recursions here, which is why I like this example. You're getting used to recursion. Let's start using it more. So now I want to find the next prime. Given that I've already found this prime, I'm going to say max prime plus 1, saying this is the next prime to check. And we want to check if this is a prime. And give me all the primes that I already know about. And then that should return the next prime. Prepend that to all the primes that we've already found. And that should be fine as long as find prime is correct. So I want to check if this is a prime, is the next prime given all these primes. To do that, I'm going to check, and if you're liking functional programming, check out this line here. I'm going to check if I is not divisible by any of the primes that I already know about, then this is prime. This is the next prime, and return it. If it's divisible by any of those primes, check the next number. So as long as the next prime exists, I'm getting closer to my base case, and I'm eventually going to find the next prime just by checking each prime up the list. By no means is this the most efficient way to find primes, but it works, and it gets to show off immutability and recursion, two examples of recursion in the same example. So that's why I'm going to compute them this way. So let's we go through this, and I want to start, again, skipping the stuff that we've already seen. We've already seen recursion on the stack. So find first n primes of 3 is going to end up calling first n primes of 2, which is ending up calling first n primes of 1. And then once n is 1 and we have these frames on the stack, we're going to create a list containing just the value 2, since we've hit our base case of 1, and create that on the heap. We create a list of ints with the value 2 only, put it on the heap, and return a reference to that list. Clarification: called a Boolean on a function value in an if statement. I don't know what you mean by that. So we're going to create this list on the heap, and notice this is the only time I can't really say that. So we're creating a brand new list, and since lists are immutable, this list is never going to change. This list will always be the same because it is immutable. We're going to return that back up to this stack frame. So return a reference to that list that we just created. Get that reference, store it in this new list n-1 primes. That gets a reference to @1. And then we're going to make our recursive call here. Put a recursive call on the stack. The first value we're checking is 3. So max prime is 2. There's only one thing in this list. The max is 2. Add 1 to it. The next value we're going to check to see if its prime is 3. And lo and behold, 3 is not divisible by 2. So we hit our base case, and we're going to return I. We're going to return 3 and say this is the next prime. And then 3 is going to be prepended to n-1 primes. n-1 primes is @1. So we're going to go to @1 and prepend this list the value 3. Lists are immutable. This list will never change. So prepending is actually creating a brand new list with the value 3 prepended to it. So we create a brand new list and then return a reference to that list. So this is going to return that reference @2 to the new list that we created containing 3 and 2. And then that's what's returned back up to the next frame, this frame with n of 3, with n equal to 3. And was waiting for that recursive call. The recursive call returns the reference @2. And then when we get back to this stack frame, I'll go back to that slide. We get back to the stack frame. It called first n primes of 2. We traced through the execution of that and saw that this did return a reference to a list containing 3 and 2, which are, the first 2 primes, as we would expect. So we did actually get the correct answer here. And now we're going to find the next prime, which should be 5, and then return that. The important note here, this never changed. I said I'd mention this again. This is when I mention it again. When you have immutable objects on the heap, they can never change. So any other part of my program that has a reference to a list never has to worry about me interfering with that list. So if I can make changes, I can't make changes to the list, but I can simulate changes to that list. If I'm given a reference to a list, I can prepend and append and remove values. I can do whatever I want with that list. But every time I make a change, it's just simulated by creating a brand new list with that change reflected. So we don't actually ever change it. We use that to our advantage, where if I have a data structure, I have a list of 100 elements, and I don't want anybody changing this list at all. I give it to a method, and that method decides it's going to sort the list. I don't have to worry about the list actually changing that I gave it, because when they sorted, they actually created a brand new list with the same elements but in sorted order. Lists are immutable. They cannot change We can only create new lists. So we can create new lists and then assign them to new values and variables, but we have to create a brand new list and then reassign. This is why when you have your loops and you have a list that's collecting a bunch of values that you're appending, you have to create that list as a var, which means the value in it can change. The value is just a reference. So when you reassign to a list, you're reassigning a reference to a new list. You're not changing that list at all because you cannot change these lists. They cannot change. So, and then we get to our return. I already covered that slide and backed up. And next we get, okay, first n primes in this stack frame is at 2, which is 3 and 2. The max is 3. We're going to start at 4 here. 4, and then 3 and 2, we're going to pass a reference at 2, all the known primes, and we're going to check 4. 4 is divisible by 2, so this resolves to false. Well, this resolves to true, and then not, so it's false. And we're going to hit our recursive step. Recursive step checks the next prime, the next candidate, the next integer in the natural ordering, which is 5. 5, not divisible by 3 or 2. So we're going to return 5. We're going to return that back up the recursion. We had 2 frames for find prime on the stack. This one was just waiting for that return value of 5. Technically, this is tail recursion, so we wouldn't have this stack frame here, but I don't, that's garbage collection and tail recursion are 2 topics that, on the lab quizzes, pretend that those don't exist. If you do understand them, pretend they don't exist. I'll try to give you questions where it wouldn't matter anyway. If you want to talk about garbage collection, that's fine, I guess. But I want to know that you know how recursive calls work with stack frames. And the tail recursion would eliminate a bunch of stack frames. So I'll try to remember to not give you any of those on the quizzes. Anyway, this returns 5 up the recursion, returns 5 up the recursion, and gets back to this. Returns 5, prepends that to at 2, which is 3 and 2, creates a brand new list with 5 prepended to it, returns a reference to that list, and then the main method is going to get this reference at 3. So we created 3 different lists throughout the execution of this program. Each time we prepended to a list or created a brand new list, as we did with the base case. So we created 3 new lists. The other 2 lists still exist, but we're only really concerned about this last one that we created, this one with 5, 3, and 2 all prepended to it. And quick side note for those of you who are thinking about garbage collection, these lists actually do not get garbage collected, which is a topic that we'll talk about next week when we talk about linked lists. The short story of that is this at 3 actually only stores the value 5 and then a reference to at 2. At 2 only stores 3 and a reference to at 1. And then at 1 only stores 2 and then a reference to nothing, indicating the end of a list. So we're not actually, when we prepend, we're not actually creating a whole new list. We're just creating the prepended element and then referring to the old list. So some fancy stuff we can do with linked lists to save some space. That's why prepend, we can't do the same thing with append, but again, next week's topic. We'll talk all about linked lists and then print them to the screen. Again, we're not doing anything fun with these programs. We're just, printing stuff to the screen so something happens. I hate this brand new keyboard. I don't think that's something that needs all of our attention. Also, your talk about 199 or 191, it's not relevant to lecture. All it does is distract me while I'm going through the content. I don't want to ignore chat because there's often good questions in there. So when you're talking about 191 or graphics cards and stuff like that, it just has nothing to do with lecture. I can't stop you. I could, but I'm not going to stop you, but could you just try to be, aware of that? G8. Oh yeah, that's what I knew there was something that I said I would talk about after. Genetic algorithm is what it is, what I wanted to talk about. So genetic algorithm does come with a GUI just like the other ones. Comes with a way to test. Just going to take forever to load, apparently. So, do you have something specific with ML? Yeah, now we're talking about graphics cards again. I don't know why that 3090 comes up so often. Everybody's obsessed with that thing right now. Xeonotry, all lecture questions are easy. I hate to say it, but I mean, there are some that are trickier than others, like factoring and for the time, alliterations is tough. Just because at that point in the semester, you're still getting used to Scala. And I guess the same thing with factoring. Factoring isn't hard. It's just, at that point, you're still learning Scala syntax. But, I don't really give you hard lecture questions. I'm sure that's not how many of you feel, just based on the lack of progress in the class. But lecture questions aren't designed to be hard. They're just designed to say, did you understand today's lecture? And can you actually apply it to code? So if today's was easy, it means you understood the lecture. And usually if somebody's in office hours asking about the lecture question, I can ask them questions about the lecture content that I covered in lecture. And they have a fundamental misunderstanding in like 99% of cases. They're not difficult, but they do make you think. Yeah, that's exactly what I'm going for with lecture questions. So lecture questions, like the softer version of lecture questions is like top hat questions. And I don't think that's an effective way to learn anything. It doesn't make you think at all. You barely have to pay attention, especially when we give you half the points just for answering. Like that doesn't help you learn. Lecture questions are designed to make you think about the content that was covered in lecture. Streaming 24/7. I do have to sleep at some point. Yeah, exactly. Top Hat sucks. But I won't even say that, but the way we use Top Hat, it can do more, but the way we use, and when I've used Top Hat, we usually just give multiple choice questions and half credit for answering. We use it as glorified attendance, let's be honest. Is there a specific question about genetic algorithm? Is what I'm looking in chat for. Did the class get caught up? No. It's a short answer. No, it didn't. So I'm obviously not going to play the whole video. It's up to you. But the demo, when you run the demo as a web server and open up the web client, this tower should always hit you. So this tower, if you don't change direction, this tower will lead you and actually aim and hit you wherever you're going. So if we go to jessehartloff.com, which uses the same code, like if I go by these towers and I don't change direction, they're shooting the AI. They're going to lead me and they're going to hit me. So they're designed to hit a moving target. And this is actually using my genetic algorithm solution for this code. So they're going to lead me and hit me. If I change direction, so I can, outsmart these towers. So once they shoot, if I change direction, they're not going to hit me. That's what C is doing when she's, So when C is moving around a lot, come on. One misclick and I go through all that. So C is dodging these, but the tower is leading and aiming to hit a moving target. As long as that target maintains its current velocity, it's going to hit. So this code for this is given to you. It's calling your genetic algorithm. So once you get your genetic algorithm running, you can run that GUI. And of course, for your homework demo, your interview, they're going to ask you, the TA is going to ask you to load that up and show you, and show them, the bullets hitting the player. So you have that way to test at least. And then you can kind of outsmart these towers when you know how they work. Every time they fire, just do a little stutter step. And you can get to the goal. Because they're expecting you to maintain your current velocity after they shoot. So the genetic algorithm homework itself, that's the GUI that you can use to test. I have this broken down in testing objectives. And the third one, I basically just say run the GUI. There's no test suite. I used to have you make a test suite for that aimbot, but it's so much physics involved that students were spending a lot of time just setting up their test cases. I don't see a real need to put you through that because it doesn't have anything to do with functional programming. But the testing opportunities, the first one is just a single value where, I got to back up and explain what a genetic algorithm is. So a genetic algorithm is going to find an optimization, an approximate solution to an optimization problem in a very generic way. So you can give a genetic algorithm any inputs and any problem to solve, and your genetic algorithm should be able to solve that problem. So if I go to geometry, so if I go to like single value, this is the simplest case, the simplest test, of course, is the first one, where what we're going to give your genetic algorithm is a cost function which takes one potential solution in the solution space and returns a cost for that, where your goal is to find the solution that minimizes the cost, and an incubator which takes a list of doubles and returns a potential solution in the solution space. So for this one, we're trying to find the perfect single value. It's just a single double, but we wrapped it up in this way that it fits the protocol for the genetic algorithm. So the genetic algorithm takes a type parameter. If I'm using single value, the type parameter is single value. But since it's a type parameter, we can't use any single value specific functionality inside the genetic algorithm. The genetic algorithm is going to work off of these lists of doubles, which we'll call genes, which is going to give instructions on kind of like genetic code on how to create a solution, or sometimes we refer to them as animals, and get in, embrace the whole genetic, the whole survival of the fittest idea. So we get this list of genes. In this case, it's going to be a list of size 1. We're just going to take the one gene, and that's directly the single value, the double that we're guessing. So if we have a list of doubles, a list of genes, which is just a single gene, that's going to be the single value. And this method is going to create that single value from a list of doubles just by taking the only value, and that's exactly the double that's in the single value. The cost function is going to take a single value and return a double, and the cost function is created dynamically. So we give the cost function the solution that we expect in this case, the number that the genetic algorithm is supposed to guess, and 30-second limit for each test. If you're running more than 30 seconds, you're going to get sick of waiting for it in IntelliJ too. It's not too restrictive because you don't want to wait that long either when you test locally. You want to wait 30 seconds every time you hit the go button. That's long. So we give it a number that we're trying to guess, and then the cost function has to take just a single value and return a double. So this method is going to return a function with that number built into it, just like Monday's lecture question. So this is going to take a single value that we want to test, and then compute the absolute value of the difference between that number's value and the number that we're supposed to guess. And for this one, I give you a sample test just to make sure we're all on the same page of how this thing works. Is if I want to guess the value 50, which is hidden to your genetic algorithm, the genetic algorithm can't just read this number or else it would just return 50. It would optimize the problem immediately. But we do give it a cost function. So we get the incubator method. We get the cost function for that specific hidden value. So this returns a function that takes a single value object and returns a double based on how far away it is from the hidden number, and then the number of genes, which is 1 in this case. Call your genetic algorithm on those values, and we should get a value that's close enough to that hidden number to be considered equal. I have, for my epsilon, I increased them for the genetic algorithm because you won't always dial in exactly on the solution. So I usually get a little bit more generous with epsilon, as you should, but not too generous. If you're within 0.05 in 2 dimensions for the line thing, the line tests, you should be okay. So the genetic algorithm itself is going to take the incubator. So we have a type parameter t. For that example I just went through, it's going to be the single value. It's going to take an incubator. For the single value, it's going to take a list of doubles of size 1 and return a new single value. And a cost function which takes the type, which in the example single value, and returns a double. So the incubator and the cost function that we saw fit this protocol, but we have to have it fit this exact protocol. It takes a list of doubles and returns a t, takes a t and returns a double. And we combine these two, and we can take a list of doubles and return a double computing its cost, which is a measure of how good or bad that those genes are. And also the number of genes, which is the size of this list. So when your algorithm runs, you take the list of genes, create a random, at least one random list of doubles. I suggest creating 100 lists of this size, but create lists of doubles of this size, and then compute their costs, take the lowest cost solution or cost solutions, and then you would iterate, but in our case recurse, and take the best ones, add some randomness to the picture. I won't go through all the details, but they're in the document in the video, and create the next generation of potential solutions, the next generation's gene pool, and try to narrow in to the least cost function that you can find. And then doing the same thing for lines, but I don't give you the testing code. You have to compute what's a cost function. So given a list of points, how do I compute the cost of a line to see how well it fits that list of points and turn that into a score? And we're going to use the sum of the squared distances of those points to the line. So how far away is each point in the y direction to that line, and take the sum of the squares of those distances. In an incubator, how do I go from a list of doubles to a line? Well, that list of doubles, just to make sure we're on the same page, that's going to be a size 2. The size of the genes, the size of the, the number of dimensions. It's going to be 2 because we need a slope and a y-intercept now. So we need 2 values to be able to set those 2 values for a line. So how do we go from a list of 2 doubles to a line? Probably going to call this constructor with one of those as the slope and one as the y-intercept. And the way things are set up, it actually doesn't matter which one you use for which, as long as you're consistent. So building those, and then I give you some sample test cases for the line. So for this set of points, given those set of points with the incubator and the cost function, your genetic algorithm should be able to find the line that best fits these points. These points are all exactly on the same line. So you can compute what the slope and y-intercept of that line, and then your genetic algorithm better return that line, or at least close to that line, because there does exist a line with cost 0. For the next 2 test cases, these points do not all lie on a line. So these points are all slightly off of a line. So your best fitting line is going to have a non-zero cost. This is something that caused a lot of issues last semester. Students had their base case of their recursion, a set of genes with cost 0. Well, that doesn't always exist. So you have infinite recursion, you time out in Autolab, and everything breaks. So I made sure I gave you the test cases just to make sure we avoid that one. And for this one, I even give you the expected line just to make sure we're using the same cost for distance functions for that. And then the third test case, I don't give you the line, and these points do not all lie on the same line. What I recommend for this one is actually computing the best fit line from somewhere else using Excel or an online calculator or something. Find the best fitting line, and then use that as another test case. If you are having trouble setting up these test cases, come to office hours. We'll be happy to help you out to understand how to use the genetic algorithm. If you're having trouble with your genetic algorithm and you come to office hours and you do not have these test cases, for my office hours, I'm going to look for test case 3, if you assuming you have the other ones. And I'm going to look for your computed line, your expected line for these points. If you haven't even computed the expected best fit for this line, I mean, that's just straight math. You don't even have to know any computer science for that. You could do that in high school. If you haven't even done that, I might not even answer your questions. Just to give you a heads up on that. I'm going to tell my TAs to do the same. I've told them the same thing. Like, if you don't have the test cases, we don't have a pre-lab that's pushing you to write these test cases. So if you post on Piazza or ask us questions in office hours and you haven't bothered to do it yourself, I mean, your question better be about test cases. Which I have that warning in every one. We do that in each one, but more so here since Autolab isn't checking your test cases. And the rest is actually building your genetic algorithm. So the primary objective is just building the genetic algorithm. This isn't structured like the other homeworks where the 3 objectives, the numbered objectives, build towards the final objective. There's only one objective here. It's make the genetic algorithm and make it accurate. And then the rest is just to help you test that thing. Oh my goodness, it's 301 already. 440, 301 for 442. So, good luck. Good luck on the genetic algorithm. It's a tough homework. Take it seriously. Start early. If you're starting close to the deadline, you're not going to get it.